3I Atlas is actually some type of alien technology sent here from another solar system.
A comet from another star has entered our solar system, and it refuses to follow the rules. NASA confirmed that 3I Atlas carries a tail unlike any ever recorded, pointing toward the sun instead of away from it. To make things stranger, its plume is dense, focused, and persistent, more like controlled thrust than drifting dust. The chemistry behind it is just as shocking, raising new questions about where this object came from and how it works. What force could drive a comet to act this way? A visitor with records to break. On July 1st, 2025, astronomers scanning the southern sky at the Atlas survey in Chile logged something so fast and so strange that even veteran observers paused. A streak of light cutting through the starfield at 130,000 miles per hour refused to behave like an ordinary comet or asteroid. Its orbit was too steep, its speed too high, and its trajectory told a simple story. It didn't belong here. Within hours, NASA's press office confirmed it. The third interstellar object ever detected, officially designated 3IATLAS. To put this in perspective, humanity had only just confirmed its first interstellar visitor in 2017, the oddly shaped Oumuamua, and its second in 2019, the textbook Comet 2I/Borisov. In less than a decade, we suddenly had a third. But unlike its predecessors, 3IATLAS wasn't just an outlier. It shattered records. Its orbital eccentricity is measured over 6 times higher than the bare minimum that defines an interstellar trajectory. Most comets swing around the sun on gentle ellipses. Even unbound visitors from deep space usually hover just above eccentricities of 1. But this object cut through the solar system almost like a straight line, a near-perfect hyperbola that barely curved under the sun's pull. The alignment threw more than a chill into the imaginings. In contrast to intercepting at an arbitrary angle, 3I Atlas arrived almost parallel with the solar system plane, being tilted just 5 degrees from Earth's orbital plane. Statistically, it seems that such good fortune, with respect to alignment, is less than 500 to 1 against. In other words, this was more than an interstellar object passing through. It was threading a cosmic needle in a retrograde motion opposite the established highway of planets. As the orbital simulations started rolling in, scientists realized that this trajectory would threaten 3 major planets in rapid succession: Mars in October 2025, followed weeks later by Venus, and then Jupiter the following March. For planetary dynamicists, those alignments were jaw-dropping. Rarely does random interstellar debris come this close to so many planets with such a sequence. By the time the tail anomaly had hit front-page news, 3IATLAS was already making scientists rethink everything they thought they knew about interstellar drifters. Its immense speed over 58 kilometers per second with respect to the Sun suggests that it has been drifting on some inconceivable timescale through our galaxy, ejected from its birth system. With a brightness visible to the medium-built telescopes almost instantly, it hinted at a nucleus large and volatile enough to withstand an accelerated plunge through the inner solar system. As for the trajectory, no other casual interstellar could have afforded astronomers around the globe the chance to track it for months with such resolution. The day after being discovered, NASA and the Minor Planets Center consulted on observing campaigns. Both halves of the globe brought dozens of other facilities to bear upon this newcomer: Gemini South in Chile, Lowell Observatory in Arizona. Even the Hubble Space Telescope was scheduled to take a closer look and hoped to resolve fine details in its growing coma. Every telescope came back with the same message. This was not an ordinary comet. It was bright, active, and full of surprises. The excitement was lush with scientific potential. Here was a piece from another star system turned into a time capsule containing the chemistry and structure shaped under alien conditions. The images, the data, every 100th of data promised to sharpen our understanding of how distant suns formed their worlds. But against celebration came the whispering, early images didn't fit quite the script. There was something wrong with the tail.
I mean, this is just directly from the telescope right now.
You're looking at a piece of what would have become a planet.
And that anomaly would soon dominate the story, because 3IATLAS wasn't just leaving a trail of dust, it was pushing material in the one direction physics says it never should, straight toward the sun. The tail that points the wrong way. For centuries, comets have obeyed the same simple rule. Their tails always point away from the sun. This is because solar radiation acts like a relentless wind, sweeping dust and gas outward into long, glowing streams. No matter the comet, no matter its path, the physics is consistent. That's why the first detailed images of 3IATLAS shocked astronomers. Instead of a classic antisolar tail, the new visitor displayed a bright, persistent plume extending toward the sun. At first, researchers thought it might be an illusion, perhaps a trick of perspective, or a temporary outburst that just happened to align oddly. But the data kept stacking up. Gemini South in Chile captured it. Lowell Observatory in Arizona confirmed it, and Hubble's high-resolution images removed all doubt. The plume was anchored on the sunward side of the nucleus, holding its shape day after day. Veteran comet researcher Bryce Bolin put it bluntly, "The plume is blobby, and it's going sunward." In comet science, that statement is almost heresy. Dust grains ejected from a nucleus are lightweight, easily pushed away by photons streaming from the sun. That's why comet tails resemble windsocks in space. To get particles moving against that push, something else has to provide force, something far stronger than sunlight's pressure. Yet here was an interstellar comet ejecting material as though it had chosen to spray into the headwind. The comparisons came quickly. Astronomers likened it to driving through a rainstorm. The raindrops always streak backward, never forward. If you saw water flying ahead of the windshield, you'd know something unnatural was happening. That was the exact conundrum facing scientists. Dust shouldn't flow sunward, unless it wasn't ordinary dust. Then came simulations. In them, teams varied particle sizes, gas velocities, and solar wind strengths in their models. No normal set of settings could produce a narrow sunward plume that lasted for weeks. Rather, the only way to get the effect back was to say that the launch of heavy grains at high speed in a very tightly concentrated jet was acceptable. The rationale for that was such that light, fluffy dust would scatter out or curve in flight under the pressure of radiation. But dense particles naturally would have retained sufficient integrity against the influence of photons when strongly seeded as a narrow jet. This was no straightforward parameter. Heavy dust needs a lot of energy for acceleration, however. In normal comets, sublimated water ice provides performance to lift only small particles, not those heavy lumps. Intense and highly directional outgassing had to be credited for the 3IATLAS plume. This would mean the comet's surface had been venting in a manner which astronomers rarely witnessed, or probably never. There is precious little old here, actually. The persistence of the plume deepened more mystery. Natural outbursts in comets are usually chaotic, short-lived. Brief flares caused by a patch of volatile ice cracking open, and the whole sunward plume held its shape in any frame of the 3IATLAS before the time window of weeks spent watching. Almost disciplined. The feature wasn't a fluke, it was the characteristic one. For planetary scientists, such an anomaly could not be just a curious happenstance. It was a challenge to the very models that guided comet studies for decades. If an object's origins in the interstellar medium could repeatedly break the rules, maybe those rules were too strict. Possible processes, chemistries, structures, or release mechanisms just had not come to us within Earth's backyard exposure. And yet, whispers began to cross the threshold to outside the conferences themselves. The focused sunward direction of the plume stubbornly reminded some of something much closer to home. A thruster plume, an articulated plume of a spacecraft. Official language remained cautious, of course. The evolving term was non-gravitational perturbation, but the resemblance was hard to unsee. The key to the mystery might not lie in the plume's direction at all, but in what it was made of, because when scientists measured its chemistry, the numbers rewrote the script of comet composition. chemistry from another nursery. If the plume's direction unsettled astronomers, its chemistry turned that unease into astonishment. In August 2025, the James Webb Space Telescope targeted 3Ia TLAS with its near-infrared spectrograph.
3I Atlas was discovered on July 1st by the NASA-funded Discovery using their telescope at Rio Hurtado in Chile.
The results stunned even veteran comet specialists. Instead of water dominating the gases, as is normal for comets, carbon dioxide overwhelmed everything. The ratio was extraordinary. For every unit of water released, there were about 8 units of carbon dioxide. Most solar system comets fall between 0.1 and 2. Over the next few days, a handful stretches to 4. Only one, C/2016 R2, ever came close. Atlas's ratio placed it 4 standard deviations beyond the norm, a true statistical outlier. The JWST team, led by Martin Cordiner, confirmed the numbers by mapping the coma at 3.3 astronomical units. More revealing than the ratio was the distribution. Carbon dioxide clustered on the sunward side, exactly where telescopes recorded the persistent plume. The chemistry and the anomaly were linked. Instead of water vapor lofting fine dust, torrents of carbon dioxide were blasting heavier grains outward in a focused jet. Surprises kept coming. Observations from the Very Large Telescope in Chile revealed strong atomic nickel streaming from the coma at levels typical only of extremely bright, volatile comets, but no sign of iron vapor appeared. Since nickel and iron usually evaporate together, this imbalance hinted at a nucleus formed under unfamiliar conditions. Nickel without iron suggested a chemical reservoir foreign to our solar system's birth environment. These fingerprints formed a vivid portrait. If Atlas had indeed accreted in a very cold area, probably in the distant ends of yet another star system, it would have preserved frozen carbon dioxide abundantly. While ice and water require deeper colds, carbon dioxide condensation can take place over the upper edges of protoplanetary disks, especially around cooler stars. This scenario would render Atlas a pristine piece of alien chemistry, deposited there eons ago, drifting in the starry skies. The implications were doubly considerable. First, astronomers now have an unmediated view of planetary nurseries beyond the Sun. Each interstellar comet becomes a messenger with its news about environments where other stars forged planets. The second implication was that the unusual chemistry offered a possible reason for ATLAS's behavior. Carbon dioxide sublimates under lower temperatures than water, which means it begins to vent earlier and much more violently from farther out in the solar system. That provided a stronger early outgassing, sustaining intense and perpendicular jets long before the comet ventured into the inner solar system. But chemistry could not explain it all. Could the outgassing really supply such a tight, permanent jet? Models found it hard to reproduce the sharp focus of the outflow because of carbon dioxide's instability and the rejection of solar radiation pressure. Carbon dioxide accounted for the energy source, but not for the mechanics. And, thus, the crux remained. Is Atlas merely some strange comet from an alien outpost in the warehouse of ice in the galaxy, flexing chemistry not familiar to us? Or did the plume hint at something more deliberate, an artifact that to the human eye resembled uncomfortably controlled propulsion? That speculation grew louder when scientists compared the plume's behavior to technology we already use, a resemblance that looked uncomfortably like the exhaust of a spacecraft's engine. Does it act like propulsion? For weeks, astronomers ran simulations to explain the stubborn plume of 3I ATLAS.
I3 Atlas. That is plenty fast to pop into and then easily escape the gravitational pull of the sun.
They tested particle sizes, spin states, and jet geometries, but the models kept failing. The only way to reproduce the observations was to assume a narrow, persistent jet-launching, relatively heavy grains with unusual precision, and that's when hesitant comparisons began surfacing. It almost looks like propulsion. To the eye of anyone familiar with spacecraft, the plume resembled the exhaust of an ion thruster. Ion propulsion is no stranger to science. NASA's Dawn spacecraft, for instance, used ion engines to travel between Vesta and Ceres. These engines ionize gas, often xenon, and accelerate particles with electric fields. The result is a narrow, collimated exhaust with a steady, gentle push. The thrust is tiny compared to chemical rockets, but in space, months of continuous acceleration yield incredible speeds. Now compare that with 3 IATLAS. Instead of a broad fan-shaped tail, like a classic comet, its plume extended in a tight arc pointing directly toward the sun. It didn't scatter or bend under radiation pressure. It held its alignment, resisting the solar wind. To many, this looked less like drifting dust and more like exhaust resisting drag. Official reports, however, remained cautious. NASA referred to the anomaly as a non-gravitational acceleration, the standard label for any force acting on a comet beyond gravity. Normal comets often experience such nudges from uneven outgassing, but Atlas was different. Its measured deviations lined up almost exactly with the direction of the plume. This wasn't random, it was directional, steady, and persistent. The numbers weighed heavily. Between July and August, the deviations from predicted paths became large, and the residuals, the deviations between predicted paths and positions. The analysts declared that the offsets were not scattered, but always pointed sunwards. When the researchers added a constant acceleration of about 4/10 of a meter per second squared, the orbital fit improved dramatically. Small, of course, but it shifted the position of the comet several kilometers after weeks of application. This is squarely within the realm of ion propulsion for spacecraft engineers. Could nature mimic this? Some would argue yes, given the nucleus was spinning just so, and the volatiles cracked carbon dioxide from a vent focused just right. This could mimic a thruster plume without all the machinery. Even then, it was a stretch. Natural jets were erratic. They flared up and then faded. They were displaced as the comet rotated. Yet, as it happened, ATLAS's plume stayed steady. The nudge consistent across datasets from Gemini, Lowell, and even amateur observatories reporting to the Minor Planet Center. This unrelenting nature invited suspicion. No one suggested Atlas was a spacecraft. Rather, its physics made easy but troubling analogies. The only thing similar we had was engineered propulsion. To observe such a close pattern echoed by a comet was both exciting as well as unnerving. It recalled the moment of Oumuamua in 2017, another interstellar traveler comprising an unexplained acceleration that fed discussions of the enigmatic solar sails and exotic ices. It was the same debate with sharper new optics, stronger data, and far fewer easy answers. Now, the same questions have come back, but with sharper images, stronger data, and far fewer easy answers, with 3 IATLAS. And all of that built toward a single moment of truth, perihelion, when Atlas would swing closest to the sun, hidden from Earth's view and perfectly placed for whatever forces were at work to reveal themselves. Perihelion, conjunction, and the watch. By late October 2025, 3I Atlas was racing toward perihelion, its closest pass to the sun. For comet watchers, perihelion is usually a gift. Sunlight at full intensity forces ices to erupt, jets to roar, and the true nature of the nucleus to show itself. If Atlas's strange sunward plume came from volatile chemistry, this was the ultimate test. But there was a curse too. Perihelion placed the comet directly behind the sun from Earth's view, in a period known as solar conjunction. And during conjunction, astronomers are blind. Solar conjunction has long been dreaded in planetary science. The sun's glare overwhelms telescopes, while its charged atmosphere scatters radio signals and scrambles detectors. For weeks, no instrument on or near Earth can provide clear data. Spacecraft near Mars or Venus routinely suffer blackouts at this time. Now, the most puzzling interstellar visitor in history was slipping behind the sun just as it reached maximum speed and activity. The timing could not have been worse. For planetary defense teams, the unease was palpable. If Atlas's plume really acted like propulsion, perihelion was the perfect moment to see it. Spacecraft engineers used the same principle, known as the Oberth effect. Timing burns at closest approach to maximize energy. A focused push here could shift ATLAS's path far more effectively than anywhere else, but Earth had no way to watch. The sound of silence was maddening. Months of data already suggested faint accelerations aligned with the plume. Now, with the comet under maximum stress, that opportunity for confirming the suggestion was ushered away behind the solar glare. For alertness, observatories around the globe had rapid follow-ups scheduled upon ATLAS's re-emergence. Gemini South and Lowell Observatory blocked out nights. Hubble reserved time. The James Webb Space Telescope stood at the ready to lock on again once the comet slipped beyond the glare. Even amateur astronomers geared up with their backyard rigs for the glint. The European Space Agency's orbiters around Mars and its planned Jupiter scans would provide additional viewpoints. Every little count, even the minimized shift in the trajectory, would testify if a plume were pure chaotic outgassing or something deliberate. Speculation filled the void. Some scientists speculated that ATLAS would crumble under solar heat, leaving behind only a fading smear. Others thought the plume would erupt into a spectacular outburst, confirming the power of carbon dioxide-driven jets. The more cautious voices looked at orbital mechanics. If the post-conjunction path did not match predictions, then a measurable push had occurred while it was hidden, and that was the cliffhanger. When Atlas emerges from behind the sun, astronomers will pore over every data point, every shift in brightness, and every deviation from script by gravity. If the orbit aligns cleanly, then the propulsion torque will fade away. However, if the track is seen to show a steady nudge, which could be explained only by a directed push, then things will get even deeper, and the dilemma surrounding the driving force behind 3IATLAS will enter a whole new, uncomfortable phase. The mystery of 3IATLAS is far from over, and the next round of data could change everything we think we know about interstellar visitors. If you found this breakdown intriguing, make sure to like, drop a comment with your thoughts, and subscribe so you don't miss the updates. And when you're done here, check out the next video showing on your screen for more stories that push the edge of science and discovery.